Good afternoon, everybody from very hot Gothenburg. I'm Minna Karstunen from Chalmers University of Technology. And before I start my talk on developing soft soil engineering skills using Class B and Class C predictions, I would like to thank Marina for inviting me to give this presentation. And also I would like to acknowledge the contributions by my colleagues from the Geotechnics research group, Yorgos and Jelke. Here is the outline of our presentation. So I will start with some background and motivation why we introduced this prediction element into our course. I will talk about the assignment, which is actually the test embankment on the right, so-called Harajoki test embankment. In the assignment, we are only considering the bit of the embankment, which is on no ground improvement. I will discuss selected results when we were running this exercise for 3 different student cohorts, and then I have some conclusions and reflections. Why we introduced this element of Class B and Class C predictions is that Sweden is a soft soil area. Here is a map of Sweden from a Swedish Geotechnical Union, which is highlighting the areas where we have occurrence of landslides, scars and gullies, and where sort of we have basically high occurrence of landslides. And you see that most of the areas where we have big cities, basically pretty much all the coastal regions, lakesides, big rivers, that's where we have high or intermediate probability for occurrence of landslides. And of course, these areas also are coinciding with areas where we have high probability of flooding. And when we combine that with the information where people travel in Sweden in terms of travel demand for vehicles per hour and the population density, we realize that Swedes are not as conservative nation as we think, because if we are looking at the west coast, east coast, and the further up the east coast to the north, these are the areas where the population is concentrated, where we have soft soil deposits and possibilities for problems with soft soils. So people tend to live in areas that are prone to flooding and landslides in Sweden. Why do we have these deposits is due to the last ice age. If we look at what it looked like in Baltic Sea during the last 15,000 years, at the end of the last ice age, there was a very thick ice cap over most of the Scandinavia. And you can see that in summer time, the region areas which are today the Gothenburg and the Helsinki were sort of not below the ice. So both Helsinki and Gothenburg were underwater. And the test site which we are using in the assignment is in Harajoki, which is 45 kilometers north of Helsinki. The Baltic Sea went through several stages after the last ice age. In the first stage, there wasn't really a proper outlet to the ocean to make Baltic Sea to be a sea. So there was a period when it was a Baltic ice lake. So the deposits under the glaciers, the rock flour and the rock flowers, which were weathered into clay minerals, were depositing in a lake environment, and you have very barbed deposits. In the next phase, there was a connection to the Atlantic when the water levels in the Atlantic rose again. And this phase, called Ioldian Sea, is a phase when the water was very cold and very salty. And that's when you sort of have clay deposits with very open structures. Next phase, the sounds of Denmark were closed because of the isostatic uplift, and there were only a few outlets to the ocean, and that's called Enkelus Lake. And then again, we get Vart Lake deposits. And finally, the last stage is called Littorina Sea. And in a way, all through these periods, this site we are talking about, which is now 50 meters above the sea level, was below the sea level. Since then, the isostatic uplift has made sure that these clay deposits are now above the sea level, and they've been subject to leaching. And because of that, we have clays which don't behave like the textbook clays. By textbook clays, I refer to these clays that if you sort of plot their one-dimensional compression, you basically have swelling index and compression index, which are pretty independent of effective stress levels. And also when you plot things in semi-log scale, you know, you don't necessarily have a very distinct yielding. When you plot for incremental odometer tests, which each of these points represent, the void ratio changes as a function of time. You get your creep index. And again, for textbook clays, the creep index on normally consolidated range is independent of time. But the clays which we have to deal with in Scandinavia are quite different from textbook clays. And this is a photo from Bualte, and this is a hand of my predecessor, Professor Göran Selfors. So the bit here, the cylinder here is a cylinder or intact Gothenburg clay. And as you see, the clay can take quite a lot of weight on it. Of course, it will deform in time, but it is still very strong. But if you disturb it, it becomes liquid, so that the consistency of Guinness. And these sort of clays are called quick clays or sensitive clays. So when I'm talking about the clays in Scandinavia, pretty much all clays in Scandinavia are clays of medium sensitivity. So due to the deposition process, which in salty environment and the leaching subsequently, they tend to have a sort of structure which is so they yield at a higher stress level than they should be. They have higher strength than they should be, but when disturbed, they become liquid. And this sort of feature affects their compressibility. So if I look at odometer test on a sensitive clay, and this clay is Vanttila clay, which is just in Helsinki area, if we have sort of multiple samples of intact clay from the same depth and we do incremental odometer tests and combine them all together, we get very consistent results that we have very high compressibility just after the yield. And it is only at the very high stress levels that we can start having the intrinsic compressibility, which the same clay has if we reconstitute it in its natural water content. And you can see that when we remold the clay in the natural water content and reconstitute it to the in-situ stress levels, which are here, we can't even get the void ratio of a natural clay. So these clays are not textbook clays. So the compressibility, the slope of a normal compression line is very dependent on the effective stress level. And same also applies to creep, that the highest creep rates occur just around the pre-consolidation pressure. Whilst when the soil is remolded or reconstituted, it has pretty much sort of a constant creep rate for backlevel purposes. So the students who are sort of designing geotechnical structures in Scandinavia, they have to be able to deal with natural soft soils rather than textbook soils. And that is why sort of we're sort of introducing these assignments. The results what I show apply to 2-degree programs. So in our old degree program, we actually didn't have that much geotechnical education compared to international courses. So we had some sort of basic course in third year following the first year engineering geology. And the third year course is pretty much the sort of a recipe. So this is how we calculate slope stability and settlement in Swedish context. So this assignment is a sort of as part of the fourth year more advanced geotechnics course. However, more recently, we renewed our degree program and we realized that with all these things, climate change, etc., it is necessary to introduce more geotechnics already in the undergraduate level. And that is sort of this course on hydrogeology and geotechnics, where we also nowadays use this assignment because this fourth year course is discontinued. And this third year course on hydrogeology and geotechnics is then sort of a natural transition for the future courses on infrastructure, where it's basically these concepts are applied in context of railway design on soft soils, and then sort of in MSc courses later on, where we go from more detailed site characterization to deep foundations and finally soil modeling and numerical analysis, also looking at how soil models are applied to natural soils. The reason we introduced this project is that when we were running this MSc course for the first time, when I arrived, we got student feedback that they felt it was very sort of abstract, that they would like to have some sort of element of project-based teaching, what they were used to in their third year. So we wanted to have some sort of project-based teaching element for the course. We wanted the students to be able to deal with real world data of real soils and basically create their own geotechnical models. And we decided that we want to do that in terms of having Class B and Class C predictions. And what I mean by Class B predictions is predictions that the students make with available soil data, but no knowledge of the field measurement results. And we also wanted to introduce an element of Class C predictions, because once the students have done their predictions, we wanted to demonstrate them that there is not just one correct solution. So there is a lot of engineering judgment you need to do in doing your predictions. And the idea of our Class C prediction is that at the end, we will give them the field monitoring data, and based on the field monitoring data, they can do improved predictions with the aid of field observations and perhaps understand what went wrong with their Class B predictions. At least that was our hypothesis. So I already mentioned that the case we chose to have is Haarajoki test embankment, because we wanted to have a case where we have access to data, both the lab data and the field data. And Haarajoki test embankment is a noise barrier, so it is a almost 3 meter high embankment, 8 meters wide and 100 meters long. And we are looking at the first 50-meter section of the embankment so that we can sort of simulate is as a sort of a symmetric problem. The embankment is stabilized by 2 berms, so students need to take that into account when they are looking at what is a stress increase due to the embankment. Loading, and in the area, the groundwater level, according to the piezometers, is roughly at the ground level, but in Finland, the groundwater variations are quite large. They can be up to 3 meters. So based on the site investigation data, they need to decide how thick the dry crust is. And then based on this site investigation data, they also need to sort of think about how thick is a soft clay deposit, which is consolidating, and underneath it is a sandy moraine, which is basically a draining layer. And the students are asked to calculate just the one-dimensional settlement at the center line of the embankment. Part of the reason we chose Haarajoki is that when the test embankment was built, there was an international settlement calculation competition. And here are the results from the settlement calculation competition, which could be classified as Class A predictions. And you see that there's a huge scatter between the predictions of the geotechnical professionals, and most of them were either significantly over-predicting or under-predicting the settlements. So there most probably was issues both with the rate of settlement and the final settlement. And obviously, some people also have taken into account the immediate settlement, which to some extent is not in the field monitoring data, because the field monitoring data only starts when the embankment is in its full height. So what we gave to the students was a cross-section of the Haarajoki embankment. And the actual embankment, which is a test embankment, is here on the right. So it is a noise barrier for the new road. And the students have here Swedish weight sounding results, field vane test results, and there is also one CPT test. And you can see that the CPT test doesn't tell much because there's hardly any tip resistance because it's such a soft soil. But with these results, basically students are able to assess where you would have the bearing stratum, where does the dry crust finish, etc. We also gave the students worked out basic index properties versus depth, based on which the students can divide the soil deposit into layers. And when you look at the density of solids data, you realize that you really have sort of deposits from these different phases of the Baltic Sea after the last ice age, because in a way, even the density of solids is changing enough to sort of affect the unit weight for a given water content. What other data we gave to the students varied. So the year 4 MSc students, we gave all the data, which involved 27 incrementally loaded oedomer tests. And we processed them, that we gave them void ratio versus effective stress data in Excel, plus plots of them in semi-log scale in case we're lazy. And we gave them 14 CRS tests. When we sort of, after having this exercise for 2 years on the MSc level, when we started our new degree program and we moved the exercise to the 3rd year, we decided that for the 3rd year students, we would need to reduce the amount of data because they also had some other assignments as part of their course related to slope stability. So we gave them only 9 incrementally loaded oedomer tests and 6 CRS tests. So what does the data look like? You see that data from 9-meter depth for hierarchy test embankment in semi-log scale. From incrementally loaded oedometer test, you have a very sort of steep initial slope, and then it sort of gets more shallow as the stresses increase. So we gave these incremental oedometer test results, and then sort of instead of asking students to derive the coefficients of consolidation from the incrementally loaded oedometer data with Taylor and Casagrande method, we decided to give them the coefficient of consolidation data from the constant rate of strain tests. The reason we do it is that we know that in Scandinavia, the incrementally loaded oedometer tests tend to give CV values which are total underestimates what is in the field. So we know that there is a better sort of resemblance with field values and lab values when you use constant rate of strain tests. But here, of course, the difficulty is again that there is a huge difference in the CV value between the over-consolidated region and normally consolidated region. So it is very important how well you are describing the pre-consolidation pressure of your soil. So the task for the students was to do settlement prediction under the test embankment. In part 1, we asked them to calculate the consolidation settlement so that they started with the basic data available, created conceptual model of a problem, thinking about embankment geometry, can you use symmetry, soil layering, groundwater table. They calculated the in situ effective stresses. They calculated the increase in total stress due to the embankment loading. And of course, because this is a serviceability limit state, there should be no traffic loading. So this is, of course, which some of the students got wrong. They had to define, using the soil data available, the necessary model parameters for settlement calculation. And finally, they needed to calculate the consolidation settlement as a function of time. So we gave them an Excel table where they should put sort of millimeters versus dates so that we could compile the results together. For MSc cohort 1, we allowed them to use whatever method they want to calculate the one-dimensional consolidation settlement. For the MSc cohort 2 and the BSc students, we decided that, okay, let's prescribe it that they should use compression index and swelling index, because by that way there is this dependency on pre-consolidation pressure for these lightly over-consolidated soils, and then sort of it links better with what's coming in the 5th year, for example, in soil modeling and numerical analysis when we go to critical state models. Once the students have returned their predictions, we gave them the measured settlements, also in Excel and of course in a plotted graph. And in addition to the settlements at the center line of the embankment, we gave them the results from 4 meters off and 9 meters off the center line on both sides. And the motivation for this one just was to highlight to the students that, in a way, this is not a millimeter game. So it is not sort of what structural engineers always think that, our accuracy is not millimeters. So we are talking about accuracies of tens of millimeters. And it is these results correspond to 3 years. So in 3 years, this 3-meter high embankment had settled about 400 millimeters. So significant settlements. In part 2, we asked the students to compare their part 1 results with real field measurements and improve the predictions with the help of these. And how we asked them to improve it, we asked them to apply Asaoka's method on field monitoring results so that they can find out whether there are differences between their predictions and the measurements was due to their predicting wrong the final settlements or the rate of consolidation. And they were also supposed to improve their predictions by rethinking the input values in the light of Asaoka's method. We gave the students a copy of Asaoka's paper, and we also introduced the method in the class. Following our experience with the first MSc cohort, we realized that it's not enough to just introduce a method. We actually needed to add a hands-on tutorial on use of the Asaoka's method so that they applied it as part of a tutorial on the data from SCORE EDBU test embankment. So those of you who are not familiar with Asaoka's method, it is one of these graphical methods where basically you divide your settlement time data into equal increments and plot your settlement at a given time against the settlement at the time -1. And the idea is that after some point that they would sort of come to a common line. And when you sort of do this interception from a line from the origin with that line, you get the gradient here of a line called beta. And with the help of beta, you are able to calculate your coefficient of consolidation in the field. It's a different value, of course, depending whether it's two-way drainage or one-way drainage. And you can also get the point of intersection is also representing the final value of a settlement when time is infinite. Here are the results for the MSc cohorts 1 and 2. What is the difference is that for MSc cohort 1, they were enabled to select their calculation method. And what we clearly see that by prescribing the method and using a method which we are using also in the tutorials, the scatter is significantly reducing. But there is perhaps a bit of a tendency to underpredict. With the BSc cohort, as I was explaining, we actually reduced the amount of data. And it seems that reducing the amount of data doesn't seem to matter that much. So we still have sort of quite a lot of results which are sort of hovering around the measured results. But we are just like for the MSc students, we get these quite gross over predictions for some students, whilst quite a lot of students are having still this tendency that they are under predicting the settlements. If we then sort of think about, is that to do with the final value of a settlement or with the rate of settlements, we analyze the results of BSc cohort a little bit more in detail. And based on numerical analysis and other researchers' predictions based on the field monitoring data, the best estimate for the final settlement is about 1.2 meters. And actually, surprisingly, many students got that final settlement prediction or something which was pretty close to that one. So we can say that the final settlement, with the exception of these outliers here, was reasonably well predicted by many of the BSc students. If we then sort of think about what were the predictions for those 3 years for which we had measurements, you see that that in a way there was a little bit of more bias on the later years when we sort of for under prediction rather than over prediction. And the results by the BSc cohort were very not so much different from this MSc cohort too. If we then combine all the results, we see that the professionals are pretty much predicting the settlements as well as our MSc cohort too. And if we take out some of these really outliers of our BSc cohort, we realize that actually the predictions by many students are as good as those by professionals. So what are my conclusions and reflections? I think introducing a project-based learning element in the course gives students experience in dealing with real data, which is not perfect, and it highlights the need for engineering judgment. So in geotechnics, we never have one right solution. It's all about judgment and interpretation. We also were aware that quite many students were doing under predictions. And we were wondering if this was due to a potential misconception in understanding the serviceability limit state design as opposed to the ultimate limit state design, because they are so familiar with ultimate limit state design that you have to take conservative values, etc. And one of our sort of hypotheses is that students ended up having low values of CC because they failed to understand that low value of CC leads to lower predicted settlements, which is totally in contrast to Young's moduli, which they have in other courses. In similar vein, students often underestimated the rate of consolidation because they chose the CV values corresponding normally consolidated range, whilst in fact the clay in the site is lightly over-consolidated, so the over-consolidation is actually about 30 kPa. So at some point, the embankment loading will take it to be normally consolidated, but it takes time to get there. What we felt is that including the real field observations data improved learning by the students. Students are confronted with feedback from reality, which is a very valuable lesson. They understand that things are not as accurate as textbooks and structural engineering assignments indicate. But what we found out that whilst the good students actually didn't really need to use Asaoka's method because they got so good predictions to start with, the students who got poor predictions were struggling with Asaoka's method, and that's why we introduced the tutorials. But still, in a way, when you have a class where you have some students who are not interested in geotechnics and some students who are not, some students will definitely struggle. What was, however, comforting that most students performed as well as professionals. And I would like to finish thanking you for listening. And if anybody is interested in these materials which we used, I will have it electronically available. And I will be most happy to answer any questions that you might have.